like this, and basically all this is as I work on this script, this updates live. So whenever I just copy in like a big chunk of something, you can just copy and paste and not have to waste time, because we're going to be pushing it to get through the rest of the lab today in terms of time.
Well, and if need be, then you have Thursday.
Yeah. Is this record? It is. All right, so we stopped down here shy of, or at number 18. So we made our model.
We actually stopped at, we haven't done 15 yet. We haven't actually interpreted. Oh no, we did.
Yeah, we did, because we got through here, and then,
We just stopped.
yeah, I stopped right where we were going to get into the probability.
We haven't interpreted, we haven't inverted odds ratios or anything yet.
Yeah, 16 we haven't done.
Okay.
Yeah.
We only got through 15.
Right on. So we have made our model. We looked at, we checked all our verifications, the linearity of the logit, where we have that interaction, with each continuous thing and its log. We've checked our baseline, correct percent classification, how many iterations, that chi-square. And let me find where I am in my other script. Let me copy over all of our stuff from number 14. All right, so that brings us down to number 16. In terms of yeah, okay. Give me a second. Let me run back through over all this, and this one, and that one, and that one. So we need to do the number 16, or?
Yeah, we just haven't talked about
Okay.
it. We ran the model and we spent some time talking about chi-square as the best method for determining which is your strongest predictor, or the log chi-square value, because the odds ratios can be a little funky. But we didn't then go back to the model to talk about how are the other predictors doing.
All right, so then if we're gonna go back to number 17 then, where we're looking at the boys versus girls, etc. All right.
We're still on 16. So yeah, we're basically interpreting this model.
Okay.
So what was our strongest predictor?
Depression.
Yeah, depression at time 1, and we saw that because it had the largest wall statistic. And the next question asked us which variables don't significantly predict depression.
Friends.
That's the only one. Everything else had a p-value less than our stated 0.05.
All right, and then just as a reminder, like I've said before, I like to run the contrast whenever I'm trying to do interpretations, just to keep straight, like, okay, males are coded as 0 and United States is coded as 0, whereas females and foreign born are 1s. So with that said, when we look back at our output, not the walled output, but the actual here, just the summary of our model. This is where we're looking at. So according to this, who is at the most risk for depression 3 years later? If we look at boys versus girls.
Can we pull up the odds ratios for that one? Says we're gonna go and interpret the odds ratios at this point.
So females would be at greater risk for.
And how much greater risk? According to that,
Here's our,
3 times.
yes, 1.53 times greater risk of developing depression than boys.
because they are coded as 1 and the group coded as 1 has 1.5 times more likely than the reference group, which is that 0, that the males. So then what about US versus foreign born?
You may wanna run that contrast again.
United States is 0. And so this is kind of hard to interpret, numerically, but as far as like knowing which is at greater risk, you should be able to tell if this is comparing the group coded as 1 relative to the group coded as 0. And if that's less than 1, what does that tell you about whether United States as 0 or foreign born as 1 is at greater risk?
United States.
Is that less risk?
Let's be really, let me take a minute here, I don't even know if I brought my stuff, but I think I did, okay, I'll just stop. We said that an odds ratio of 1 means what?
50-50.
What at 50-50?
Equally
Just-
as likely.
Good.
They're equally, each group is equally as likely to go on and gift.
Exactly, that there is an even odds, right? How's that for an oxymoron? An even odds of having the condition based on whether you're in the reference group or the alternative group, right? That there's really no greater or decreased risk based on whatever that variable is. If we have odds ratios that are greater than 1, especially, they have to be significantly greater than 1, right? They can't just be like 1.00001 and you say, oh, look, they're at higher risk. If you have odds that are significantly greater than 1, what does that mean for the group coded as 1 compared to the group coded as 0? Compared to the reference group,
Increased odds.
increased risk. So girls were 1.5 times more likely, right, to develop depression than boys. Their odds ratio is significantly greater than 1. What if you have an odds ratio that is significantly less than 1? What does that mean for, in this case, foreign born compared to our reference group, 0 US born?
Because the US is more like at risk.
What's that?
The US is at, the reference group, the US is more at risk.
Yeah, but let's keep it in the ratio, in the language of, we're always talking about the people who are coded as 1. So foreign born kids are what? Less likely to develop depression. So because the odds ratio is significantly smaller than 1, you're always talking about who the 1 group is compared to the 0 or reference group. So compared to US born kids, foreign born children were significantly less likely to develop depression. It's not as easy for us to say how much less likely, which we're gonna talk about in a little bit, but for now, that's what we need to know.
All right, so then when we look at depression, what do we make of that?
People with depression are more likely.
Right, so as depression increases at time 1, so do the odds of depression at time 2, time 3, time 2. Self-esteem.
Say it louder, Rosalie.
Low self-esteem.
People with low self-esteem. As you can tell, as self-esteem goes up, the log odds, or odds ratio, decrease. What about discrimination?
This expands more discrimination.
Correct. And then log friends.
Does it
Well,
really matter? Even odds?
yeah.
Very good, it was supposed to be a trick
They're-
question.
Right, so because that's not a significant effect there, the number of friends does not predict depression. Is everybody tracking on that?
So you've got to look at both, right? You have to look at the wall test to look at significance, and And then, if it's not significant, you know that there's no change in the risk based on that variable. Whereas if you do have significance, you then need to go to the odds ratio to say, okay, well, who's at greater risk?
Now, as far as the interpretation, like, sex is easy. It's easy to interpret. Like, women are 1.5 times more likely than men to develop this depression. But when it's smaller than 1, it's not as straightforward and intuitive to interpret, because this basically is that the United States born participants are less likely by a factor of 0.78, and so the United States is less likely.
Foreign born is less likely by a factor.
Sorry, yes. I am running a severe caffeine deficiency this morning. But like that whole by a factor of 0.78 isn't quite as intuitive to interpret as 1.5 times more likely. So if you have odds ratios that are less than 1, the easiest way to interpret them is to invert it, which literally just means 1 divided by those odds ratios. So all you have to do is here on number 18, where we want to invert these, we're just going to say, as a reminder, to get those odds ratios right here, we just exponentiate those coefficients. And so if we just do 1 divided by the exponentiation of those coefficients, when we run that, we now have the inverted odds ratios, and you notice that that birth region is now no longer 0.78, but rather it's 1.28. But when you invert it, you have to also flip the reference group, essentially. So now we're saying that foreign-born, U.S.-born, are 1.28 times more likely to develop depression than the foreign-born. Same thing with self-esteem. That was the other one, I believe, that was less than 1. Right, there we go. So whenever you see odds ratios of less than 1, just do 1 divided by those odds ratios to invert it. And then when you write that sentence, when you're interpreting those, you just have to remember to flip those interpretations around.
For the interpretation and the output of the model, are we not, back to that question about controlling for females that are U.S. born, that's the effect?
If you're talking about the log odds here, not the odds ratios, but the log odds, then yeah, your intercept would be for the log odds for males in the United States with 0 depression, 0 self-esteem, 0 discrimination, and 0 log friends. Then the log odds would be negative 2.9. But being able to intuitively understand log odds is basically impossible, which is why we interpret things in terms of those odds ratios, where we're comparing these two groups specifically relative to one another, or probability, which is what we're going to get into here in this next bit of the problem. If you're talking about absolute probability, so instead of saying, let me roll right into number 19 here.
Let me just address that one other point. In your interpretation, you are basically saying controlling for these other risk factors, girls are 1.5 times more likely to develop depression, or controlling for these other risk factors, children with lower self-esteem were 1.28 times more likely to develop depression in high school than children with higher self-esteem. So it is true that you're kind of controlling for what other risk factors are, but you're not giving an odds ratio, as Austin is putting out, only for girls who were U.S. born, who had no friends, who had no, that's not what you're doing. you're not interpreting the intercept. You're basically saying like, okay, I know there's other risk factors here, if I control for those, here's what gender does.
But again, those odds ratios give us that relative risk of, boys versus girls. But sometimes you might be interested in just knowing, well, what is the probability that pick a female, and what's the probability that that female is going to get depression, or females in general, or some other specific thing that it's not relative to boys. What are the odds of a female getting depression, but rather what is the probability that a female in this sample is going to have depression at time 2. And the other reason for probability is that probability is the only space, because you have that probability space, odds space, and log odds space as this goes through these transformations in these models. And probability is the only one that you can graph with the raw data. So if you're interested in visualizing logistic regression and you want to be able to plot what your raw data points are and then have some sort of model to be able to visualize what's going on, probability is the only visualization where you can retain the raw data. Once you're in odds or log odds, you can't. The raw data disappears. It ceases to exist. It's that weird transform data. So in order to convert the odds or log odds to probability, there's a couple different ways to do it. For one, we're going to create the same model, but we're going to include our numeric versions instead.
Can I also pause you again? I'm really sorry, I know I keep doing this.
You're fine.
And it probably just means we're gonna have class on Thursday and you guys have to, but this is important. When we talk about odds ratios, we are literally talking, as we said, about relative risk. So relative to the reference group, what's the risk for this other group? Gonna take it back to COVID-19, because why not? Now we can have a cute little acronym for it. So I recently saw a diagram that talked about what is the risk of mortality if you get coronavirus based on age bands. Have you guys seen anything about that? It sort of looks like that histogram, but in reverse. So the younger you are, basically mortality is 0. And then by the time you're in your 80s, mortality can be up to like 15-16%. If we were to compare infants to the elderly on mortality, the odds ratio for the elderly group would be something like, 30 times greater odds of dying, which sounds horrific, and it is horrific. But it doesn't tell you absolutely how many of the elderly people are gonna die who get the virus, right? To know that, you need to know probability. So saying it's 30 times greater than the elderly than in infants only tells you who's more likely to have a mortality outcome, but it doesn't tell you, what if the mortality outcome in infants is 50%, right? That's pretty terrible. What if but in this case, the mortality rate is basically 0, or almost 0. So probability, what we're gonna look at now, tells us about absolute risk, right? Complete, like what percentage of these kids are actually gonna get depression, not relative risk, who is more likely to get depression than another. Does that conceptually make sense to everybody? Alright, cool. So that's what we're gonna do now.
Alright, so I've gotten the same model from before, only I've changed birth region to birth region N, and I'll explain why. But so essentially I'm making this probability model. And there's a function called predict. And I know a lot of you are familiar with predict already, that essentially what predict does is you put in some model and you have the option to put in some new data frame, and then it will take that model and make predictions on that new data based on whatever's in the model. What that means, I'm just going to copy over a big chunk here. So if I create a data frame with just one single data point, and when I look at this prob case data frame, I have just one observation where I set the sex to male. I set everything else to the mean. So this is the mean of all the Dep 1 scores. This is the mean of birth region, the mean of SE, the mean of discrim, and the mean of log friends. And just that one thing is set to male. So now, when I use predict and I tell it that the new data is prob case, this one observation that we made, it's going to take the model that we've created, it's going to plug in 1.61 for our depth score, it's going to plug in male for the sex, birth region, it'll plug in all of these different, these mean values. So we're wanting to say, in this case, what is the probability, like controlling for everything else, that a male is going to develop depression? Then what we do is we say predict, and we'll tell it to predict based on mod prob, our probability model that we created. Our new data equals prob case, that new data frame that we created. And then the way that you get predict to output the probabilities instead of odds or log odds is you tell it type equals response.
Can you say again what type equals response does?
That is what tells us that we want the output in probability. Like the response type is the probability output.
Jake doesn't know that he can't look at that.
Oh, go to, on your browser, go to bit.ly/uark-hw3.
URK/HW3?
No, bit.ly/uark-hw3.
Okay, I think we're gonna have to get.
So this is the absolute probability that boys,
Right, because we set it to male.
and so if we wanted to do the girls,
Then
like the
you could just
boys.
switch that to female. Same thing, one of the good things about doing it this way is that you could actually model any number of things. So say if you wanted males that were born in the US specifically, then instead of putting mean of birth region here, and the reason that I switched to birth region N was so that we could take the mean, because if we left in, the reason we changed this model is if we still had birth region .f, we would have to choose one or the other because you can't average across a factor. But mathematically, you can collapse across birth region by using that numeric version and just taking the mean. But yeah, so like here you could specify like, well, what if a male that had 7.3 log friends, like whatever you put in this data frame is what gets predicted on here. So similarly, if we wanted to look across both male and female, we could do that just by creating a prob case 2 and saying the sex F is both male and female. And when we run that, sorry, and one other thing is that instead of using data frame here, I put in expand grid. What expand grid does is it creates a data frame, but whatever you put into that data frame, it crosses to give every possible combination of things. So if you say, x equals 1 through 4 and y equals a and b, expand grid will give you x1, x2, x3, x4, y1, y2, or b1, b2, whatever the thing it was that I just used. But so basically now, using expand grid, and now that we're putting in 2 values for sex F, this prob case 2 is going to give us the same thing. It's going to give us the mean, depression, birth region, et cetera, but down here under sex F, it's going to give us both of these. So we now made 2 observations. One that's for males, one that's for females. And if we plug that prob case 2 into predict, it will output 2 separate things. So now we have the probability that a male will get depression, about 14%. Probability that a female, absolute probability, will be about 20.2%.
I have 2 questions. First one is my
might just need to give a little bit of time so people can type out these things.
Okay.
And then the second question is, for the birth region N, if it's a 0 and a 1, and you do that mean, wouldn't that be 0?
Mm-mm.
The mean of zero, like all the zeros and ones, if you sum them in the column. Unless they were all US born.
Because if you have exactly 50-50, then the mean would be 0.5. If you have more zeros than ones, then it'll be less than 0.5.
Gotcha.
To make sure I'm 100% tracking with this, is basically what you're doing with the prob case data frames, basically kind of like setting a reference group to compare that absolute risk.
Yeah, what I'm wanting to do is take it, because when we look at our if we step out of logistic regression and just think of this in terms of we'll pretend like this is a normal linear regression where you have your coefficients here, and so you could say based on this that we'll even ignore what all this is, but for every 1 unit increase in whatever, there's a 0.43 increase in this, and then whatever this is, it decreases as it goes up by 1. So you could take this and write out your linear formula where that y equals, the prediction equals this variable times this coefficient plus this variable times this coefficient plus this times this, and predict does that for you. It takes all these coefficients and you just put in the specific values that you want for each of these, and then it generates that prediction. And then that type equals response says we want this prediction and probability. And so all you have to do is tell R which things you're wanting to, which values you're wanting to make that prediction for in each of these things. Does that answer your question?
And can we go back to the thing that you had the prob model? Because this is also relevant, and maybe it's part of what you were asking. The actual model. Not the case, but the prob model. You did a.
Oh, right. Sorry, that was here.
Yes. Okay, here, when we are creating this generalized linear model, what we were, no, not this one, actually, I'm sorry, you're right, we do need to go to the next one, the prob case. Okay, if we hadn't done all these specifications, like specify the probability when mean is the mean of this variable and birth region is the mean of the birth region and whatever, then the probabilities that we would have gotten would have been the probability for boys who had 0 depression, were born in the US, had no self-esteem at time 1. That's an odd boy, by the way. No friends and no discrimination. And that's not the probability we want, because doesn't describe our population. So by doing it this way, by specifying, okay, well, when all these things are at their center point, at their mean, then you can get across the whole sample what was the probability that a boy had depression at time 2. So that is exactly why we had to provide all that detail.
So, I think I'm a little confused on the output of the 1 and the 2, so I don't know which one is male and which one's female.
Well, if you look at prob case 2, 1 is male,
Oh, maybe I
2
did
is
that.
female.
Oh, I see, just
You just have
without
to
putting
run.
it in the project. I gotcha, thank you, sir.
Also, this question on the code isn't in the document for the homework.
Oh, do we not send the updated?
We might not have something updated.
Okay.
Okay, but go ahead and please report on it. It is in your syntax,
Yes.
right? In your R syntax. So that question is supposed to be in your homework. We'll send the updated Word version so you can just copy and paste it in your homework. Yeah. I tweak these every year, every time I teach it, so.
And then one last thing that I'll show you on this probability stuff before we move on is that there is another function besides predict, and by manually creating the data frame, it's from the GG effects library, and it's called GG predict. And with this one, it's a little more straightforward that you just use GG Predict, and you may need to install GG Effects package if you don't have it already. Sorry, I totally spaced out on sending out the email saying, hey, here's all the new packages you might need this week. But this essentially does the same thing, just in a more streamlined way, where you tell it, terms equals something, and then that something is what it's actually making the predictions for. I'm going to run both of these, and then we'll talk more about it. So first, I'm going to do the mod prob, which is the one that we just created, where we changed birth region to the N instead of the .f, and then the mod was the original one that we created with factors for both. So if we run ggeffects, ggpredict, we tell it mod prob terms equals sex.f. It's going to output for us the probability for males and females. And you'll notice down here it says adjusted for and gives a list of stuff. What that's telling you is whatever you don't put into the terms automatically gets controlled for at the mean. So instead of having to create a data frame manually and say, like, I want dep to equal the mean of dep, and I want this to equal the mean of whatever, it will automatically do that for you. Now, the reason that we switched it from that birth region.f to birth region.n is if we go back to the .f version by running mod, you'll see that it gives you those probabilities, but adjusted for birth region f equals United States, because that's what I was talking about earlier, that you can't average across a factor. So it will default to picking one or the other. You could specify things manually. One of the nice things about the GG effects thing is that it is really, really, really flexible. You could put in multiple terms. So if I said, sex.f and birth region, it'll cross those and it'll output 4 different things. One that's for females in the US, one that's for males in the US, one that's female foreign born, one that's US foreign born. If you have continuous things, so say we wanted to look at at self-esteem at plus and minus 1 standard deviation of the mean, beside continuous variables in the terms, you can put brackets and specify specific values for that continuous thing. So you do the math and you see that, okay, 2 and 4 is minus and plus 1 standard deviation. So you could say, SE1 bracket 2 comma 4, and then it will give you 2 separate sets of predictions, one that is for SE equals 2, one for SE equals 4. So I'm not going to get too terribly in depth with all of that. Just know that that's a thing that exists, and if you're trying to plot models like this, it can make it a lot easier, because this is what you'll need for making those visualizations. And so if we were going to visualize this logistic regression model, it would be basically what we've done before with ggplot, where we just plot our scatter points. Then you would use ggpredict or predict, leave off the new data so that it's like predicting for the actual data, and it will output your prediction plus that confidence interval high, confidence interval low. And so you'd be able to say on a separate line, like, all right, now give me a line where y equals predicted, and it will plot out that line. And then you can use geom error bars or geom ribbon and tell it that you want the high and low to be the confidence interval high and confidence interval low. And so now you'll have that scatter plot with your points, or jitter plot, along with that band and confidence interval, so that you're able to visualize the model itself. And I can...
So I'm going to suggest that we come back to GG effects. Was everyone able to install the package or get it to run? Make sure you use quotes when you try to install the package. That was the first mistake I made again. I tried to install it without quotes.
And I'll later on, I'll go back and I'll generate a plot and send out an email that demonstrates, hey, if you go back to number 19, starting here.
Yeah. Did you get it? No. It's still not working. I'm thinking is really helpful about, well, two things I want to point out about GG. First of all, it's way easier to do that than to type out your whole model and then specify the means and all that, right? Yes?
Yes.
Okay, we're all under caffeinated. And it gave you everything, and it even gave you what the means were for all the variables, so you knew what the levels were. And it gave you the two predicted probabilities, in this case for male and female. Notice those confidence intervals. Whoops.
Sorry, I was gonna go back to
Notice
it.
those confidence intervals. What can you tell me about the confidence bands? They're narrow, right? So for boys, the probability of developing depression in high school, what was the range?
Is it 12 to basically 17%?
12 to 16.6%, right? Okay. What else do you notice about the confidence intervals?
We don't know that.
Exactly. What does that also tell you?
Difference.
They're going to be significantly different if we have a 0.05 as our criteria, right? So non-overlapping confidence intervals in those predictions also tells you the same thing that the test tells you, but just visually. Really big, as you know, on interpreting your confidence intervals. Take a look at your confidence intervals and think about what do they mean for you. I think we should go back to GG effects when we do our interaction, because the other thing that's really powerful is, like, we know in general here that girls are more at risk for developing depression than boys. There's a 20% chance that a girl will develop depression by high school, whereas there's a 14% chance for the boys to do that according to the data we have. But there are other variables here that matter. And so, as we just saw in the mod you ran, which wasn't the mod prob, this now represents the probability of developing depression for who or for what? Yes, for US-born participants. So in the US-born participants, there was a 15% chance that the boys would get depression. It's a little bit higher. And a 22% chance that the girls would get depression, also a little bit higher. So if you're ever going to look at interactions, which we will do at the end of this lab, going back to your GG effects and using GG predict to be able to get what is the predicted probability for this group at this level of another variable can help you look at those risks in context. So we'll come back to that again.
All right, and sorry, another package, boot, what the fuck? Boot, B-O-O-T, will be one that we need to install. Because for the next one, the next problem is like how many cases in the data that the model doesn't fit well. And in this case, what we're going to look at is the studentized residuals that are greater than 3 standard deviations. So for this, there is, like I said, in the boot library, there is a function called GLM GLM diagnostics. And so if we put in our model from GLM diagnostics, it'll give us a lot of different stuff. As you'll see scrolling down through here, a lot of different diagnostic stuff. What you need to know is that the stuff that's called RD is what this particular function names the studentized residual. So if we run the GLM diagnostics $RD, now it will output the studentized residuals for each participant. And what we want to know is, are any of these studentized residuals greater than 3 standard deviations? And these are in standard deviations. So we just want to know, like, are any of these values greater than 3? Because that means that the studentized residuals are greater than 3 standard deviations.
And why are we looking at residuals, guys? What do residuals tell us?
The error, like
much of an error you made in prediction. And so this is another macro assessment of our model so we looked at, we're kind of going a little bit through a few different versions, but that's partly because this originally was based on SPSS and this is the output order SPSS. But we evaluated model fit overall with our chi-square. We also evaluated our Hosmer mean shell test. Another way to evaluate the quality of a model is we looked at iterations, how quickly did it converge on a solution. And now we're looking at mistakes, how much error we're making. And so specifically we're trying to see whether and how many people have a studentized residual of 3 or more, or greater than 3, because that tells us that how many people were doing a shitty job at predicting their probability or their risk for depression at time 2. We don't want to have these. We want to have none of these if possible.
All right, so if this outputs the residuals for everybody and we want to see if it's greater than 3, when we add on greater than 3, it now turns it into a logical test where it'll output a bunch of, trues and or falses. And so in order to summarize that, easily, just wrap that in table and it'll create a table and we see that everyone is false. There are no trues. So none of these studentized residuals are greater than 3, which tells us what? No.
It's hard to interpret mumble.
Model fit well for everyone.
At least there are no concerning outliers in a sense. Still hear lots of typing. That's going to give me a different. All right, so then we move on to a moderation analysis. And so here is where we start looking at our interactions. The first thing that we'll do though is it asks you to report the means of DEP, SE, and Discrim, and this might be another place if we sent out the old document that things don't line up because we made some changes. The script, the R script is correct, so just go off of that more so than the document for now. So the first thing we're going to do is we're going to look at the means of all of these and mean center each of these variables. And so we'll create dep1.c, se1.c, and discrim1.c, with .c just being my personal convention for this means it's a centered variable. So in terms of getting those means and stuff, we all should know by this point about 1,000 different ways to do that. But we'll say we take our data frame and we pipe in, we're going to select those 3 variables that we're interested in, which are dep1, se1, and discrim1. And then pipe that into summarize all and tell it we want the mean. And so we see that the mean of dep1 is 1.63, the mean of se1 is 3.37, and the mean of discrim1 is 2.89. So as far as reporting that on the homework, and then like I said, we'll need to create these centered variables. So we take our df, we're going to mutate to create these new variables, and we'll say se1.c equals the mean of se1, comma, dep1c equals the mean of dep1, and discrim1.c
Is it? Is doing it actually creating S1C where everyone?
Oh,
is
sorry,
at
sorry. I'm
value?
missing an important piece here.
Okay.
It's SE1 minus the mean of.
Otherwise, we would just end up with a whole list of means.
Yep, sorry about that.
Everybody would have a constant then.
Oh, it's just one of
For
those.
some reason I'm getting an error that says it could not find the function of the pipe, and I don't understand why.
Did-
You have to load.
Did you load tidyverse at the beginning?
Yep, I had to do it again when I loaded the boot.
It's weird. Yeah, I did
Every
load it
time I
at the
sit
beginning.
down, I don't understand why I'm not on a cord. I think I just have electric power.
Okay, thank you.
So once I run, oh god damn it. So now we're just taking each SE value and subtracting the mean, each depth value, subtracting the mean, each discrim value, subtracting the mean. Once we run it to make sure that the code is working correctly, come back in and reassign that to the data frame. So now we've created our 3 new variables. And then while y'all are finishing up on that, the problem that we have is we're curious if birth region interacts with depression, self-esteem, and discrimination to predict depression at time 2. And so that we're wanting to model the interaction of each of these 3 continuous variables with birth region. So the way that we'll do that is we'll have the same model from before, but now instead of dep1, se1, and discrim1, we'll change those to those centered variables, and then we'll also add in each of those interactions. So this top line is the same as what we had before, except these are the .c versions. And then we'll also add in the 3 interactions that we're interested in. And as a reminder, the way you annotate a specific interaction explicitly is just putting a colon between the 2 variables that you want to interact. So birthregion.f colon dep1.c is the interaction between birth region and centered depression. Birthregion.f colon se1c is that interaction between birth region and centered self-esteem, etc. But the rest of this model is the same, and I'm just calling this one mod int. Who can remember how we check for multicollinearity in these models? VIF and tolerance. Exactly. So here for number 22, we want to check multicollinearity. We'll use VIF for mod int. And then if we want to check our tolerance, it'll be 1 divided by that VIF. Let me create some space here. And so when we look at our variance inflation factor, what values are we looking for in these 2 things?
Anything over 2?
You're thinking of skewness, I think.
No, it was like either one. Over 0.1.
For tolerance, we're looking for greater than 0.1,
And less than 10.
less than 10 for our VIF.
Yeah. If you have values of VIF greater than 10, you've got a problem, meaning that you've got some redundancy in your variables, and it's going to create instability in your model.
And
Because tolerance is just 1 over VIF, the reciprocal, right? The reciprocal of 10 is 0.1. So these really are very, like, they're literally completely redundant, but for whatever reason, you're supposed to report both. You're supposed to say at least that you checked multicollinearity by examining variance inflation factors and tolerance values, even though they're 100% redundant.
So tolerance is just a VAF without being inverted?
No,
Or other way.
No, tolerance is the inverted VAF.
So then, our multiclinearity looks good, so we run our model. And we can look at our model summary. And then this basically proceeds as we did before. Before we get into like actually looking at these, the next problem us has to first look at that omnibus, chi-square. Does anybody recall how you get that chi-square from this information? Basically, that omnibus test is comparing our model to a null model, so a model without any parameters in it. Exactly. We're wanting to compare this deviance, which conceptually think of that as, the way you would think of error in a regular linear regression, that sum of squared errors. It's conceptually similar. So we're wanting to compare our null deviance, the deviance of that null model, to the deviance of our full model. So the difference between deviance here will be the actual chi-square statistic. The difference in degrees of freedom will be the chi-square degrees of freedom. And then in order to get that p-value, use that p chi-square function, which would look something like this. So our mod int null deviance minus mod int deviance. So this would be chi, well then our degrees of freedom, so chi 9 degrees of freedom equals 223.95. And then for the p-value, we just put in that chi-square statistic, those degrees of freedom, tell it lower tail is false, and we see that our p-value is substantially less than 0.001. That step will come in the next portion when we get into the actual hierarchical, because in this case there is only one step. We just do it all at once. But if you're doing nested models, then you'll have like this stuff entered at step 1, other stuff entered at step 2, and then you're wanting to compare like, was the change significant between step 1 and step 2, and as you work your way through this series of nesting. So for now, there's just the one step.
So let's pause for a moment and talk about what do we have in our new model. First of all, what is our new model concerned with? What are we trying to understand? What interactions in particular are we interested in? Because we already ran most of this model, so what's new here?
Birth region, depression interaction, the birth region by self-esteem interaction, the birth region by discrimination.
Right, so we're basically now concerned with whether birth region, meaning whether we have some moderating effects, right? This is looking at moderation between birth region and a few of our all of our continuous predictors that were significant. Okay. We could have done friends one too, but friends one frankly is a garbage variable. We just threw it in there so that we felt good that we transformed it at some point. But, okay, so we're looking at birth region times depression. We're looking at birth region times self-esteem. and birth region times discrimination. And what do you think we're kind of trying to figure out here? Because all of these things are trying to predict what? Risk for depression in high school, right? Okay. So we already found the main effect of birth region, and we also found main effects for all of these variables. So now we're asking the question of like, well, we already know there's a risk, but do these things interact with each other? So does being foreign born with depression interact with depression to predict risk for depression? Or does being US born interact with self-esteem for depression? Or does it interact with how you experience discrimination? Or how that discrimination impacts you, right? So we're trying to really up our ante here by examining the potential moderating effects of one of our variables, birth region. R is really freaking powerful. I finally found a perfect analogy for how I think R, like what is R? Because it struck me forever that I was like, I don't fucking understand the data frame when I first started working on it. I don't understand the data frame. Why do you need all these packages? This is like so weird. Can't you just give me a freaking chi-square when I run an analysis? Do I really have to type in all this extra shit? So R is my workbench, right? My data frame are my raw materials, and my packages are my tools. I mean, that's how and so I'm trying to construct these models. And I need different tools for different parts of my model, right? But the tools themselves are not useful unless I have these raw materials. So that's like my way of understanding what is R and what are the pieces of R. And so for whatever reason, the tool that we have to understand logistic regression is great at giving us the details, but it doesn't give us out the gate, which now I understand why people write their own packages. Because like the first thing I want to do now is go write a supplemental package for R so that we can just type in something like model chi-square in the Anna is awesome package, and then you get your chi-square without having to type that whole long shit that we just did. So.
I mean, that's the LM support package was developed at Wisconsin, and that's like the main thing we used across the GLM course, because it's like all these tools that are specifically for this one type of analysis. That's like, oh, you need to do all this really useful shit.
And you don't want to have to type in 14 lines of code to get one thing, right? So like now suddenly the need for a new tool is making a lot of sense to me. So, but that's what we just did. So now here's the output of what we got. Now where's the output of what we got? Did you run them yet?
Yeah. Oh, that's it. Oh, for the chi?
Yeah.
It's right here.
Okay, can someone please interpret for me what we got and how would we write it down? If you're reporting it in a paper, right, you ran your model, how would you report your model overall fit?
I'm unsure what the null model is here in this case.
We do not want the null model. The null model is no prediction, just base rate.
So this would, I guess, broadly say that our interaction model did better than the null model.
Yeah, so in all these predictors as a whole, which includes the interaction terms, right?
Mm-hmm.
But how would you actually report that? So you say, yes, the model was significant. Well, I don't know. We haven't even talked about that. Was the model significant?
Yes. Yeah.
Okay. So let's compose the components here. Chi-square,
Degrees of freedom 9
9 degrees of freedom.
equals 223.95.
Okay, can someone other than Noah, who has clearly got this, help me out here? I didn't actually use it.
223.95. P-value less than 0.001.
That is what you're gonna report in your analysis, in your manuscript. It took you all of that just to be able to generate that little part of your results, right? The model as a whole was significant. You'll see this written up in your TNF book. And this is how you report that overall model. We also often add our pseudo effect size measure, which I think is the next place we're gonna go. my favorite word, think of the universe. Okay.
Austin, what packages is pseudo-R for?
Pseudo R squared is in the desk tools package, I believe.
Is there a different function that can get back produced?
Oh, is yours having problems installing that particular thing? I can probably find one. I don't know off the top of my head, but remind me, shoot me an email, and I'll dig around. Because I mean, I'm sure there is. There's a library for just about anything. But yeah, so to report that, Nagelkirkey's pseudo R squared, just using this function, and we see that our pseudo R squared is 0.15.
Yeah, we
The-
had point, wait, 0.01, 0.09, and
Is it
point.
2? 2.5?
0.25, right, corresponding with the correlations of 0.1, 0.3, and 0.5.
And we report Nagelkirkey. Oh,
Yes.
Thank you.
Which I didn't finish writing down. I will.
And now for this next portion on number 24, it's just asking to report all the micro assessment stuff. And it would be, all the same things that we did on the previous model, only now we're using mod int instead of mod. So from summary, we can get those estimates. We get our walled statistics using ANOVA and telling it test equals walled, type equals 3. For our odds ratios, we're going to exponentiate the coefficients. We'll invert those odds ratios so that for the values that are less than 1, they're easier to interpret. And then for those confidence intervals of the odds ratios or inverted odds ratios, instead of exponentiating just the coefficients for the model itself, will exponentiate the confidence intervals of those models. I also wrap that in round and with a 2 just so that it rounds off to 2 decimal places on those to make it a little bit cleaner. But these lines of code right here will give you all the information that you need to fill in that table on number 24.
Let's pause for a moment.
Yeah.
I think what we'll do, after we go through 25, I think we're gonna save the hierarchical for Thursday.
Mhm.
We have to.
Yeah.
So I'm sorry to have teased you with the no class, just kidding. But it will probably be a reduced class, and that also means that your assignment will be due on Thursday, a week from Thursday, not a week from today.
Just to make sure I got it, on the round with the 1 over the x, is that the probability?
The inverted odds ratio, or the 95% confidence interval of the inverted odds ratio.
And you only worry about the inverted odds ratios if it helps you interpret. Make sure that you put the right odds ratio in a table. So for example, if you were doing foreign born and US born, remember foreign born had a smaller odds ratio, smaller than 1. So as long as you put in your table foreign born, or you put in your table note, birth region coded, so 0 was US born, 1 was foreign born, make sure you report the 0.78 estimate, not the 1.24 or whatever it was estimate.
How would you feel about annotating and putting in the inverted odds ratios, but just annotating that like this isn't the inverted odds ratio.
I would feel that it's better to write in, US born,
Okay.
or to have like actually done the 0, 1. So if you were going to put in the inverted odds ratio, don't call it foreign born 1.24 asterisk. But make it clear that the reference group is US, is now foreign born. But in text, I often have my tables with those regular ones, but in the text I'll say, you know, foreign born, whatever odds ratio, blah, 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 meaning that if children born in the US were 1.24 times more likely.
All right, so again, we've got our estimates here. If we look at our walled statistics, what does this tell us about moderation happening in this model or not?
Only a moderation between birth region and discrimination.
Right, and what is that relationship? What is?
Someone other than Nova. Just to make sure we're all catching up with you.
Well, let's look at our odds ratios too.
Some of that, there's a significant difference in where you're from, resulting in different degrees of discrimination, which is predicted after depression, time to in high school.
I'm sorry, can you say that again?
So depending on where you're from, it's gonna result in different levels of discrimination, which is significantly predictive of your depression at time 2.
Not quite. What you described, I think, is a little bit more mediation. Like, I think what you described was depending on where you're born, you might experience different levels of discrimination, which would elevate your risk for depression. But we didn't test that. So what's the difference? That's more like mediating, like the reason why one group might be more at risk is because of this
So-
other intervening variable. How would you instead describe moderation between these two variables?
I might have misheard him, but I thought that he said that like the way discrimination affects you may depend on.
Is that what you said?
Yeah, you different levels of discrimination depending on where you're born.
So he's
Okay,
talking
yeah,
about,
no, oh, yeah,
you're right.
that's,
So no.
so off by just a little bit.
Central and South America is one, right?
Mhm.
The rest is so isn't it saying that if you are from, it's saying that as you increase in discrimination, if you are from Central America, then you would be experiencing
Let's not try to
slightly
interpret,
less.
yeah, let's not try to interpret the direction yet as much as in general, what is a moderating effect telling us?
what effect discrimination has differentially on US versus Central American, South American born people.
At different levels of, another variable is
Discrimination for depression.
Yeah, so the way discrimination predicts depression is different for kids who were US born than for kids who were foreign born. That's like fundamentally the way to talk about moderation, is that the relation between a variable X and a variable Y depends on their level at this other variable moderator. So we still don't totally know how that interaction looks. We're gonna talk about that next, but that's fundamentally what we found is the relation between self-esteem on depression, that was the same whether you were US born or foreign born. How current depression affected risk of future depression, that was also the same for US and foreign born. But how discrimination impacted you, well, that depends. That depends on where you were born, at least in this group of kids.
terms of interpretations, it would basically proceed the same as you would interpret, a standard linear model as far as thinking about like, all right, so the difference between like this interaction will tell you, let's ignore that it's like these estimates are actually in log odds and we'll just call it the effect. And so the effect of discrimination switching from the 0 group, that reference group, to the 1, it is lower by 0.51. So in other words, for those foreign-born participants, the ones who are coded as 1, the effect of discrimination is lower amongst that particular group. Where things can get kind of confusing is now when you get away from just calling it the effect and try to like put more concrete terms on it and thinking in terms of, well, this is the log odds are lower by 0.51. Switching that to the odds ratio or inverted odds ratio, or going to that probability space. That's where you really have to stop and make sure that you're connecting the right dots and following that right thing. But in general, as long as you can remember that when you're looking at these tables and you know that, okay, so discrimination has less of an effect for foreign-born than for U.S.-born, and then on the back end, sit down and figure out, like, okay, now what are the actual changes in these odds ratios and such, which would be from...
There's less of an information on foreign.
Yeah, so basically it seems, given this data, it seems that people who are foreign-born, that like discrimination doesn't affect them as much as U.S.-born.
Or it's not as predictive of depression.
There we go.
So one of the ways that we can figure this out, and I know we're out of time here, but imagine if you plotted, these are the predicted odds or predicted probabilities actually of developing depression. So predicted prob of depression for 2 groups, US-born and foreign-born, at levels 1, 2, 3, and 4 of discrimination experiences. This is a way you could visualize it. We're not going to do that today. You could do that with the DFX thing that we talked about. But imagine in general, the more discrimination, right, the more depression, the more likelihood of depression. What the negative value in that interaction term told us is that this line is probably, I don't know where it starts, but it's probably less sloped. It's not that discrimination doesn't matter. It does. It probably elevates your risk for all groups, but its relative elevation in one group is lower, in the foreign-born group is lower than in the reference group. So I don't know that this is what it would look like. We could plot that. But the negative coefficient in that interaction term tells you that as discrimination increases, its increase in depression is less or dampened in the foreign-born group compared to the